Okay, so in this video, I'm going to go over enthalpy and energy use basics. So we're kind of wrapping up this discussion of enthalpy and psychrometrics and look at how dehumidifying air, how HVAC equipment is used to dehumidify air, and then how the implications for energy use, but also a little bit about occupant comfort and how temperature and relative humidity impact that. And also we'll go over some sort of novel applications to reduce the energy use of dehumidifying and cooling air down with Ervs and Hrvs. Okay, so there's a lot of different ways that air can be dehumidified, but the primary way it's done is through cooling. So you can have a window unit, you can have a central unit, and a lot of commercial buildings have these packaged units. Okay, so it's called a package unit. In this case, an RTU because it's a rooftop unit. And this is sitting on a roof. So this is really, really common in commercial buildings in the U.S. So I'm not going to get into too much detail about this because we'll go over this in a later time, but I do want to introduce this type of system to you. So this is an all-in-one. It has all of the refrigeration, vapor compression refrigeration cycle elements in here. So inside of here are condensing coils, there's evaporator coils, there's a compressor, and there's an expansion valve. So it's all of those things in one single unit. And so there's actually coils here, and there's a fan at the top that pulls air across the coils, okay? And that's going to be your condenser coils. So basically what happens is you have air. So let's say you're in an office in the middle of the summer, somewhere underneath here. So that air is going to come up here. It's too warm, right? You want to cool it down. So it comes up here, goes through the compressor, then goes into these condenser coils, right? And so when you condense, you release heat from that air out, right? And so there's a fan up here that blows air out across these coils. And so it pulls heat from the air and dumps it outside, right? Then it goes somewhere in here, there's going to be evaporator coils. And what happens in the evaporator coils, remember you have to vaporize the refrigerant, you have to add heat to it. So what happens is you take heat from the air in here, and this is a fresh air, this is outside air damper here, so this allows outside air to come in if you need fresh air. If you don't need any fresh air, then you can just circulate the interior indoor air through this system, and these can close off depending on the type of system you have. And so we dump heat out here, and then what happens here, we absorb heat from the air around it, because in order to vaporize, okay, because the evaporator coils are there, we need to absorb heat, which cools down the air. And then there's a ductwork and an air handler that just blows cold air down. So that's just the basics of it. We'll go over this in more detail later on. But the point is you have warm air that comes in here, condenses, dumps some of that heat out, comes over here, pulls heat from the air, and that makes the air cold, and then you blow the air down through the ductwork here. And so all of this, in this evaporator step, you end up cooling down the air to the point, or you may cool down the air drop it down below the dew point, which then creates liquid water. And that's why you see these condensate lines on all air conditioning units, right? So there's a condensate line in the back of a window unit. If you have a central air system, wherever it is, there's going to be a condensate line coming from that as well. And that is because when the evaporator when it cools down the air, you can drop it below the dew point, which then causes condensation. And so let's look at how that works on a psychrometric chart and how much energy it takes to actually do that. So there's actually a way you can calculate how much energy it takes to cool air down. It's a pretty simple equation, okay? And the equation is 1.08 times the cubic feet per minute of whatever the airflow is times the change in temperature. So if I want to cool 1,000 cubic feet per minute of air, right? So we have a fan that's taking 1,000 cubic feet per minute out of the building or out of the room, right? And then it's cooling that down from 75 degrees Fahrenheit, dry bulb, at 60% relative humidity. So we have 75-degree air, 60% relative humidity, and we want to just cool it down to 64 degrees. So how much energy does that take? And we can use this very simple equation. 1.08 times CFM, which is 1,000, times the delta T, which is 75 minus 64. That gives us 11. And so 11,880 BTU. So BTUH is BTUs per hour. Okay? So if I want to cool 1,000 cubic feet per minute of air from 75 degrees Fahrenheit at 60% relative humidity to 64 degrees, it's going to take about 12,000 BTUs per hour. So if it's 10 hours, that's 120,000 BTUs and so forth. So if there's a constant stream of 1,000 CFM, that's how much it's going to take. And if you think about an air conditioning system, that's kind of what's happening, right? Like the air is constantly warming up inside the building, and so you need to cool it down. So there can be this constant airflow with an air conditioning system. So we can also use enthalpy to calculate this, and the enthalpy calculation is 4.5 times CFM times delta H, right? So this is delta T, this is delta H. Remember, H is enthalpy. So we can apply the same thing, and if we use our chart, it's going to come out to about the same number. You know, I use the chart here, and it's like difficult to get exact numbers, but it's going to be about the same. Okay, so 4.5 times CFM times delta H. All right. So it takes a lot of energy to dehumidify air, and we'll go over that here in a minute. All right, so now let's say, so this equation, just to go back up real quick, this equation here is only if there's no condensation, okay? Now you can use this equation if there's no condensation as well, right? But this one you can only use if there's no condensation, and let's go over that. So if we have the same air, it's 1,000 CFM, now it's 90 degrees Fahrenheit, so like a hot, humid day, 90 degrees, dry bulb, 80% relative humidity, okay? And we want to drop that down to 50. So this is pretty typical in an air conditioning unit. We're going to drop it down to like 50, 55, okay? So if we go to the chart, and I'm not going to go over that because we've already done that. If I would go over to my chart, I would see that at 90 degrees Fahrenheit, 80% relative humidity, it's going to be, if I go from that to 50, right, so I go all the way to a 50 degree dry bulb here, okay, it's going to drop to 32 BTUs per pound, right? So our delta H is 32. Okay, so our delta H is 32 in that situation. So let's calculate, if we ignored condensation and we ignored enthalpy, how would we calculate it, right? So we have 1,000 CFM, we go from 90 to 50. So if we calculate that, that's about 43,000 BTUs per hour. Okay, but that's actually, you can't do that. And here's why. If I cool, if you look on this chart over here, right, we're going from 90 degrees and 80% relative humidity. Okay, so we're going here, and let's go up. I'm sorry. Where are we? 80%. Looks like it's right here, right? Okay, so that's where we are here, right? So we have this much absolute humidity. So what we're doing is we're going across, and then we're going down until we hit 50, right? So here's 50. Okay, so now we're here. So you can see that up here our enthalpy is about that, and down here we've lost a lot of enthalpy, right? And also our absolute humidity has dropped from here to about here. Okay, so from here to here. So we've lost moisture. We've lost moisture out of the air, and we've gone over. I went over that in a previous video, so make sure you watch that. Okay, so from here, this is where we started. This is where we ended up. We lost moisture. Okay, and the delta. We've also lost enthalpy. We've gone from here to here in terms of enthalpy, and we've lost about 32 BTUs per pound. Okay, so the point is we have reduced our humidity in the air, right? We went from here to here. We reduced our humidity. So when that happens, you can't use this equation because there's all this latent heat in there that we had to get rid of, right? The enthalpy dropped significantly. And that's because both the temperature dropped and also because we went from here to here. So we lost all this moisture, which means we had to use energy to eliminate that moisture. So the proper way to calculate it, okay, is using this equation. So if we use that same scenario, right, so we have, remember the equation is 4.5 times CFM times delta H. So in this scenario, we have 4.5 times 1,000 cubic feet per minute, and our delta H is 32, right? Oh, I put the wrong number in there, but anyway, it'll be about the same, right? So regardless of 32, and it's going to be, the point is it's much, much higher. So look how much higher this is than that 43,000. So the point is that if we lose, okay, if we dehumidify, we have to remove additional latent heat. And so if there's dehumidification, if we drop below the dew point, that means we have to use this equation in order to accurately account for all of the energy that's used in cooling that down. The point is that this uses a lot of energy. So it takes a lot of energy to dehumidify the air. And so that needs to be accounted for when we design our systems. And I mean, you have to pay for that energy, right? Okay, so we'll practice that in the lab this week. And so there are some ways around some of this, okay, because it does take a lot of energy to cool air down, heat it up, and also to dehumidify. So you can use ERVs and HRVs. So an HRV will be here on the left. And so the way an HRV works, or heat recovery ventilator, it really just, the key to this is the heat exchanger here. And so if you think about the airflow in this, let's do a little, all right. So right now we're inside, okay, and we're taking, in this case, cool air inside. So we're in the middle of a warm day, right? So we cool the air down, the air's cool inside. Well, what we're doing is we have to bring in order to bring in fresh air, we need a ventilation system, okay? And so this brings in fresh air. So we've talked about a number of times, when you bring in fresh air, you have to heat it and cool it, okay? And that's a problem. So what this does is it takes this, right now we have to get rid of this stale air because we need fresh air, right? So we bring out the cool air. At the same time, we bring in the warm, moist air, okay? And so what happens is it goes through this heat exchanger here, okay? And so these air streams don't mix, but there's metal plates in here that allow them to exchange heat. And in this case, it actually exchanged some moisture as well. But now we have this warm air coming in, right? And it goes through, and what happens is, if we have a heat exchanger here where the cold air and the warm air can exchange heat, what's going to happen is the heat, instead of this heat coming right in, this hot air coming all the way into the inside, this heat is then going to absorb into this cooler air, and it's going to warm that air up before it's emitted from the unit, right? So we start out with cold air, and normally the cold air would just go right out and we'd bring warm air right in. But if we can use a heat exchanger, we can actually absorb some of this heat, dump it into this cold air before it goes outside. So it basically pre-cools the air coming in, okay? And in the winter, it's the reverse, right? So we have warm air going out. That, if we need fresh air, we're blowing warm air out. What's going to happen is that's going to cross the cold air coming in, and the heat is going to go into the cold air and preheat the cold air. So these things are great because they can just do the same thing. They do what you want no matter what the season is. And so with an ERV, or an excuse me, where are we? Click that. With an ERV, it also absorbs moisture, right? So now you have, again, let's say we're in the summer and we have cool air inside that's not very humid, right? And then we're bringing in this humid, warm outside air. So now we have this wheel, this desiccant wheel, that does the same thing, and it basically acts as our heat exchanger, but it also, what it does is it takes moisture from this outside air that would normally be dumped into the space, and then you have to dehumidify it. What it does is it dumps some of that moisture into that air going out. Okay, it dumps moisture into the air going out, which dehumidifies the air. So an ERV will preheat air in the winter and pre-cool air in the summer for ventilation. And the ERV, what did I say? The HRV does that. The ERV does both humidity and temperature. So it evens out. So it dehumidifies warm, moist outdoor air, and it'll actually add moisture to cool winter air, which helps because then the building's not too dry. So again, the beauty of this thing is you just put it up, and no matter what the season is, it will do what you want it to do. And I mean, this really makes a difference because this can have a heat transfer coefficient of up to like 75%, right? Meaning if I'm taking, I can take, like, if I'm in the summer, I can remove about 75% of the heat coming in and dump it out before it even goes in the building, which saves me a lot of energy, right? And so there's your close-up of a desiccant wheel. So why do we care? There's actually some interesting research on how much time we spend inside of buildings. So feel free to press pause about how much of our lives do we spend inside of buildings. And the answer is about 87%. So about 87% of our respective lives we spend in buildings, whether it's at work or at home or wherever, whatever, going out to restaurants and so forth. So we spend a lot of time in buildings. So the space conditioning in a building, the temperature and relative humidity is really important. And there's some other reasons that improved indoor air quality can reduce productivity in businesses. If you're running a business, you want people to be comfortable because they can actually increase their productivity, your bottom line. There's also improved employee comfort and satisfaction, health, work performance. So all these things, you can just imagine, right? You're in a building. Just think if you're in school, right? And it's really hot and really humid in there, like you're not getting as much work done. You're not able to focus. You're not able to get much done. So a comfortable indoor air quality is really important. And there's a video that's posted, so make sure you watch that. But there's this sort of recognized comfort zones. Generally between 35 and 50% relative humidity is comfortable. Somewhere around, we'll call it 65 to 75. It depends on who you ask, but that's your sort of comfort zone. Not everybody falls into this, but this is a general rule of thumb. Like if you're in here in the winter, you're okay. If you're in this area in the summer, you're okay. And we'll investigate that more in a lab. Right, so comfort, and also humidity, lack of humidity helps prevent mold and mildew, which is a big deal. And then also it has a very important impact on the size of your HVAC system, so your heating and cooling capacity, which has cost implications as well. So all of that is really important. So humidity, just humidity in general, we don't tend to think about it a whole lot. We think about temperature, right? That's where our thermostats are set. But humidity is a really important part of being comfortable. It's an important part of a safe and durable building. And it's a very important part of sizing your HVAC equipment. So to summarize this discussion, remember that anything that cools the air is going to end up dehumidifying it, right? So package unit, rooftop unit, a window unit, whatever. Okay, so if you drop below the dew point, you're going to release moisture, which then dehumidifies the air. If we don't have condensation and we want to calculate the energy that we need to cool down air, we can just use 1.08 times CFM times delta T. If there's any condensation, or there happens to be evaporation, which really doesn't happen, but you would use the sensible heat loss equation. The heat loss equation using enthalpy, which is 4.5 times CFM times delta H. Remember that an ERV and HRV, they basically are ways to bring in fresh air and minimize the cooling and dehumidification that you have to do to that air. And remember that it not only does it take energy to remove heat from air, but it takes a lot of energy to dehumidify air. And finally, occupant comfort is a very important consideration. Okay, and so now you hopefully have some sense of how HVAC equipment is used to dehumidify air, how you calculate that energy use. Also some idea why occupant comfort is important, basics of how an ERV and HRV work, and then you should have some understanding of a typical comfort range for temperature and relative humidity.